Good evening. This is week 4 of Applied Thermodynamics course. I am Bharat Aditya, a BMRF scholar from IIT Madras. So I'll be taking the week 4 course today, and this week we are looking at the components of the steam turbines, the types of steam turbines, the type of condenser, and the type of boiler, and we also look at the nozzles which are used in the turbine. So we'll be looking at that, and we'll see some multiple choice questions and also some numericals on that. So this week, if you see the turbines, we saw two kinds of turbines. One is a reaction turbine and one is an impulse turbine. And we also will look at nozzles. And if you see in boilers, we'll compare these two turbines in the coming slides. We'll also look at boilers. We have two types of boilers. We have water tube boilers, and there's another one which is called as a fire tube boilers. And if you see, come to condenser, we have a surface condenser and a direct contact type condenser. So starting, we'll see first let's understand on the condenser. After a turbine, if you have expanded, it's being operating in a closed cycle. So the water before pumping to the boiler, converting it to steam, you have to condense it to increase the pressure. So what you do is you use a condenser. So this condenser can be of two types. One is surface condenser. As the name suggests, the water condenses on a surface. So it's like a general heat exchanger. We have the fluids, one of the cooling medium will be normal cooling water available, so that will be sent through the tubes, and the steam which is coming out of the turbine will be passed over the tubes, and as this will be at a lower temperature, so the water will condense on the surface of the tubes and it will be collected. So this is surface type condenser, and you have a direct contact type condenser. In this case, you mix the fluids, so because of this mixing there will be reduction and the water will condense. So these are the two types of condensers. One is a direct contact. The fluids will come in contact, they are mixed with. In surface, they will be separated by a surface. So that's the major difference between the two. If you see in direct contact types, the medium is about the fluid which you are mixing with the steam, water which you are mixing with the steam, which has to be pure. You cannot be impure with it because it will be carried on through the loop. But if you look at surface condenser, there is no restriction as such, even though it may reduce the heat transfer coefficient by depositing on the surface. And that can happen, but there is no such a restriction because it is being separated. So that is a limitation. And we'll move on. We'll see with the turbines. As I said previously, we have two types of turbines. One is an impulse turbine and one is a reaction turbine. So the name is comes from the action which is happening on the steam. So in case of steam turbine, if you see as the image on the right side, I have a nozzle, and then there is a turbine impeller. So what happens? This high pressure steam passes through the nozzle. If you see at the bottom part of the impulse turbine, the green part is shown as the fixed nozzle, and this red curved part are the blades of the turbine. So when the high pressure steam passes through the nozzle, you can see there is a steam pressure. When it's coming it's at higher pressure. When it passes through the nozzle, the pressure drops. So at the exit, the pressure is at a lower value compared to the previous inlet. And if you see, the reduction in pressure causes an increase in velocity of the steam. So this increase in velocity of the steam will be a high velocity. So this steam goes and hits on the turbine blades, and the steam will be redirected. So because of which the direction change, there will be impulse created. So hence the name impulse turbine. So this is the general phenomena of how the impulse turbine works. But if you look at a reaction turbine, this has both a moving blade and a fixed blade, but in this case both will have a pressure drop. And as if you see, compare the pressure diagram and velocity diagram, the pressure reduction is not as much as what happened in the impulse turbine. So the velocity will be also lower compared to what it achieved in the impulse turbine. And even if you see in the blades, there will be reduction in pressure happening, but in impulse turbine, if you see, there is a pressure is constant when it passes through the turbine blades. But in case of reaction turbine, there is a reduction in pressure, also a reduction in velocity. So in the impulse turbine, during the blades there is no pressure drop, only velocity drops. But in case of a reaction turbine, both pressure and velocity drops in case of reaction turbine. And if you see a comparison, I have compared in the table that all pressure drops, this is what listed out the differences. All pressure drops in the nozzles, no pressure drop in moving blades. Same in the titles is reversed. It's impulse turbine and reaction turbine. I have written it the other way around. So all pressure drops in the nozzles, no pressure drop in moving blades is for impulse turbine. So pressure drop occurs in both the nozzles and in moving blades. And if you see impulse effect of the steam jet, but in case of reaction turbine, impulse effect plus reaction force of exiting steam both have effect. Because here there is no pressure drop, here there is a pressure drop, so there will be a pressure difference which will cause an reaction force. So that's what here it's only because of the velocity. Here it's because impulse turbine, it's only because of the velocity, that direction change in direction of the velocity is causing force. But in reaction turbine, both velocity and pressure will cause will generate a force. So hence the name reaction. There is a reaction force because of the pressure. So impulse effect plus reaction force in the exiting stream is for reaction turbine. Then high jet velocity and high blade velocity. So there will be high jet and high blade velocity. But in case of reaction turbine, there will be low jet velocity and low blade velocity, as I said previously, and as you can see from that graphs. And another difference you can see is the pressure operating of the moving blades is at lower pressure compared to the reaction turbine. The pressure is higher compared to the previous impulse turbine. And also you will require a large number of stages in reaction turbine to achieve the same output for which you get from an impulse turbine. And if you see the degree of reaction, so degree of reaction is the change in enthalpy in the moving blade divided by the total enthalpy change in the fixed and moving blade. So that is the reaction degree of reaction for a stage. So if you see for an impulse turbine, the moving blade, there is no change, so that will be 0. So we can say that degree of reaction will be 0 for impulse turbine. But the reaction turbine reaction may vary from 0 to 1. And we saw that this high pressure steam was passing through the nozzle. So we look at some characteristics of nozzle. So before understanding nozzle, we need to understand that sonic velocity, that is the speed of sound origin. So that is defined as is square root of dp by d rho. So differentiation of pressure with respect to density will give you c square, or sonic velocity square. And Mach number is defined by velocity of that fluid compared to your sonic velocity. So v by c, which will give you Mach number. So when a fluid passes through a nozzle, you get a relation with the Mach number, velocity and the area. So that is given by dA by A equals m square minus 1 into dV by V. So this is the relation you obtain. And so we have considered 3 cases here. One, a converging second a diverging, third a converging and diverging nozzle. So we have three cases here. So what happens is when so case 1 is when Mach number is less than 1. So dV you will have consider that Mach number is less than 1. So in that case your m square value will be lower than 1, because Mach number 1 B equals to C, so this will be less than 1. So this that you get a negative value. So dA by A equals to minus dV by V. Okay, so when your area is reducing, so your velocity will increase. So your flow at the inlet will be at subsonic condition, and it will accelerate, and your velocity will increase at the exit. But if your Mach number is greater than 1, so this quantity will be positive. So if the case is a converging passage, what will happen is your velocity will decrease at the exit. So in case of a converging nozzle, if your Mach number is less than 1, your velocity at the exit will be greater than what it was at inlet, and it will be a nozzle. It will act as a nozzle. But if correspondingly pressure will reduce. But if your velocity, if your Mach number is high, your velocity is very high at the inlet, it will reduce. If Mach number is greater than 1, so at exit it will be at lesser value. So this will act as a diffuser. But if you consider a diverging nozzle, the same case, your dA value will be positive. So when your m square value is positive, so Mach number is greater than 1, your velocity will increase, because dA by A, so m square, this quantity m square minus 1 will be positive for supersonic flow. So dV by V, so dA, if dA is positive, dV will also be positive. So for a diverging nozzle, dA will be positive, so hence the velocity will increase. And if the Mach number is less than 1, the reverse will be the case. So your velocity will decrease and it will act as a diffuser. So that's the case listed. Case 1, when Mach number is less than 1, converging passage will act as a nozzle, but a diverging passage will act as a diffuser, as I explained. And if you have Mach number greater than 1, converging passage will act as a diffuser, but a diverging passage will act as a nozzle. So what will happen if you have a converging diverging nozzle? So in that case, you are at the throat section where you will have a least area, there you will have Mach number 1, and at inlet, if you have subsonic flow, it will reach Mach number 1, and it will become supersonic at the exit. So that's the case. Then we have seen nozzle. Now let's move to boilers. We have seen condenser, we have seen turbine, and turbine also has a nozzle. We have seen nozzle. Now moving on to boiler. Boiler, we have two types of boiler. One is a, as I told earlier, a water tube boiler and a fire tube boiler. The name itself suggests what's happening. So in case of a water tube boiler, water is inside the tube, and in case of fire tube boiler, the furnace hot gases are inside the tube. So that's the two cases. So if you see in the first case, for a fire tube boiler, you have a furnace, hot gas is passing through the tubes, and it's enclosed in a shell with water inside, and because of heat transfer, your water is converting to steam and it's taken up. But in case of an water tube boiler, let's say this is the other way around. In the shell side, you have hot gases passing, and in the tube side you have water which is coming. So this hot gases, there's heat transfer happening because of the convection majorly, and conduction in the surface, and then the water boils inside the tubes, and steam is collected out. So that's the difference in the boilers. One is the first is hot gas passing through the tubes, and the waters passing in the tubes. So the hot flue gas through tubes, it takes more time to start steam generation after firing the boiler, because you have to heat the whole water which is present, and then you do you take it to boiling temperature, and then it will start converting to steam. So that initially will take some time. So rate of steam generation is lower, so it will generate only low pressure steams up to 20 bar, and see it's suitable for heating in chemical process and also for process steam. And if you, in case of an water tube boiler, so water passes through the tubes, so it will be heated by hot gases around, and it takes less time compared to the fire tube boilers, and the rate is also higher compared to what you get in the fire tube boilers. So it can generate high pressure steams and up to 200 bar, and this is suitable for high capacity power generation. So that's the difference between the two types of boilers. So let's move on to see some problems. So we have an impulse turbine, and 4 options are listed out. So it says an absolute velocity at the inlet of moving blade is equal to that at the outlet. It says the relative velocity at the inlet of the moving blade is equal to that at the outlet. C, axial velocity at the inlet is equal to that at the outlet, and whirl velocity at the inlet is equal to that at the outlet. So out of the 4, the options is answer B. The relative velocity will be same in case of an impulse turbine, and in a reaction turbine it will increase. So for that this case, for ideal case, in this is true only when for an ideal case, because you consider there is no friction, so there will be no change in relative velocity. So the answer is option B. The relative velocity of the inlet of the moving blade is equal to that at the outlet. So moving on to next question. In a Molière diagram, constant pressure lines is dashed from one another. So options are maintain equal distance, B diverge, C converge, D nothing can be said. So the Molière diagram is the HS diagram, enthalpy and entropy diagram, and in that case, how will the constant pressure line look? So that's what is been asked. So if you see, I've plotted a HS diagram for a water steam. This blue line, the dark blue line, gives you the dryness fraction 1. So it's converted totally into steam, and this blue lines gives you constant dryness fraction. So this is 1, this is 0.95, 0.9, and so on. This green lines gives you the constant temperature lines, and this constant red lines is the constant pressure lines. So in the case of diagram, if you want to go, if you look at the diagram and answer, see, if you see, if you consider constant pressure at lower temperature, your difference between two lines is less compared to at the rightmost part. So rightmost part you have a larger difference, and compared to the at lower entropies. So you can see, say it's diverging, but if you don't have a Molière diagram, will you see? So then you can use the TDS relations. dH is TdS minus VdP. In that case, so dH minus ds, because you are taking pressure as constant, so the other part will be 0, so that will give you temperature. So when your pressures are larger, your temperature will also be larger, saturation temperature will also be larger. So if you are at a normal, you can see normal water boils at 100 degrees at the atmospheric condition, 1 atmosphere. But if you increase the pressure, it will boil at larger temperature. So the saturation pressure will be larger for higher saturation temperature. So for constant pressure lines, the slope for dH by ds will also be large when the temperature is more. So that difference you can see. So you can conclude that it will diverge. I hope this is clear. Okay. So next question is there's a assertion and reason. So the question is the nozzle control governing cannot be used in reaction steam turbines, and the reason given is in reaction steam turbine full admission of steam must take place. So the options are A and R both are true, and R is the correct reason, and R is not the correct reason, and A is true, R is false. So the nozzle control, what does nozzle control mean? So governing in general, you need to run the turbine at a fixed speed, constant speed. So to do that at different load condition, you are maintaining the speed. So in case of nozzle control, you control the inlet steam using a valve, so you restrict. But in case of reaction turbine, what's happening is you need to admit full steam, because you're in case of a moving turbine, the difference is happening because of the pressure as well, and not just because of the velocity. So for that you need to admit the whole steam and not reduce the flow. So in this case both A and R are true, and R is the correct reason for A, because in nozzle you are restricting by valve, and in case of reaction turbine you cannot restrict, you need full admission of steam, so you cannot use A. So A and R are both true, and R is the correct reason. So moving on, we have a impulse staging is commonly employed in high pressure part, and reaction staging is in intermediate low pressure part of the steam turbine. Reason given is the tip leakage across moving blade is less in impulse staging, and the pressure drop is small, and there can be large pressure drop across fixed blades and nozzle. So for this case 2, A and R are both true, and R is the reason for having a impulse staging at high pressure part and reaction staging at the intermediate low pressure part. The reason is same. The high pressure part you need because you need high impulse staging occurs. You need to have high pressure in the fixed plates. You will have a reduction in pressure, so you need to have the impulse staging at high pressure part. But reaction staging we can use because there will be tip leakages there. So the options are A and R are both true, and R is the correct explanation of A. So the next question is, we have statements regarding the impulse steam turbine. We have 3 statements given, and the first statement is blade passages are of constant cross sectional area. And second is partial admission of steam is permissible. 3 is axial thrust is only due to change in flow velocity of steam at inlet and outlet of moving blade. So which of the statement is given above are correct? So blade passages of constant cross-sectional area. So in impulse turbine, the passage between this thing will be of constant cross-sectional area. So first one is true. Second is partial admission of steam is permissible. This is also true. This is not true in case of reaction turbine. And option 3 is axial thrust is only due to change in flow velocity of steam at inlet and outlet of moving blade. This is also true because the velocity you can split into two components, whirl and the vertical component flow, and your thrust is generated because of the difference in that flow. So that's what is being given. Axial thrust is only due to change in flow velocity of steam. So the whirl velocity will give you the turbine force to require to rotate, and the flow velocity is the thrust. The difference in the flow velocities will give you the thrust. So the axial thrust is generated by the flow velocity difference. So this 3 is also true. So the option A, 1, 2 and 3 all are correct. So the next is a water tube boiler has dash compared to a fire tube boiler for the same diameter and thickness of tube. A is less heating surface, B is more heating surface, C is equal heating surface, D heating surface depends on other parameters. So as we saw in the previous slide about water tube boilers and fire tube boilers, so the answer is B, more heating surface, because the water is contained in small diameter tubes and you can have multiple tubes. So the heating surface of water tube boiler will be more compared to in case of the fire tube boiler. So there will be relatively larger heating surface which is provided in terms of water tube boiler compared to the fire tube boiler. So that will give you larger surface area for heat transfer and hence more heating surface. So the answer is option B. So the next is a flow through a nozzle is regarded as a constant volume flow, constant pressure flow, isothermal flow, or D, isentropic flow. So in this case it's option D, it's isentropic flow. Thermodynamically, next is thermodynamically efficient process would involve dash exergy loss with dash rate of entropy generation. So we have to say whether minimum or maximum. So for an efficient process, thermodynamically efficient process, so this will happen when you have minimum exergy loss and minimum rate of entropy generation. So if you have entropy generation and exergy loss are related, so you can find entropy generation into T naught will give you exergy lost, the total exergy lost in the process. So one is minimum, the other is also will be minimum, and anyway you have to reduce either think in terms of entropy or in terms of exergy. You need to minimize both, either exergy loss or entropy generation. So exergy loss is basically what you are not able to get out of the system, which is you have lost to friction or lost by some other means. Exergy is the definition of exergy is that it was the maximum amount of work which you can get from the fluid which is at some temperature on pressure and a given condition when you bring it to the ambient condition, the dead state, the maximum energy which you can get it during the doing the process reversibly is exergy. So that is the maximum which you can get. But you will get you will not get the same amount, because the process in actual case will not be reversible. So you will get only some fraction of the maximum exergy which you can get. So the rest will be lost. So in terms of efficiency, your system is performing less. So if you are reducing that exergy loss, you are moving towards a more efficient process. So that answers the question. A thermodynamically efficient process would involve, so efficient process will involve a less exergy loss. So minimum exergy loss with minimum rate of entropy generation. So the next is, the pressure at which the steam leaves the nozzle is known as back pressure. The statement is true or false. So it's true. The pressure at the nozzle exit is called as back pressure. So the statement is true. If at the next question is, if at inlet of the turbine the water possesses kinetic energy as well as pressure energy, the turbine is known as a reaction turbine. The answer is true. I think we'll go back to that slide so it will be easier. See, the pressure and for reaction impulse turbine and reaction turbine have shown this pressure and velocity diagrams at the bottom. So if you see, you have lost all pressure energy and it has reached its lowest pressure in a impulse turbine, but you have high velocity. But in case of reaction turbine, you have still some pressure and the velocity, and in the moving blade there is reduction pressure and the reduction velocity, which is aiding in the impulse and reaction forces. So you possess both reaction, both pressure and velocity energy. So if you see the pressure at which, so if at the inlet of the turbine the water possesses both kinetic energy as well as pressure energy, the turbine is known as reaction turbine. So this statement is true. You have both velocity and pressure energy. So kinetic energy and pressure energy, you both have that in terms of reaction turbine, but you possess only kinetic energy in terms of in case of impulse turbine. So this statement is true. So the next question is, in impulse reaction turbine stage, the heat drop in fixed and moving blades are this is 30 kilojoules, not 39 kilojoules, 30 kilojoules and 40 kilojoules per kg respectively. The degree of reaction for the stage will be, so in fixed blade you know that heat drop is 30 kilojoule and moving blade is 40 kilojoule. The degree of reaction for the stage will be, the options are 4/7, 3/7, 1 and 7/4. You can straight away neglect 4 because it cannot be greater than 1. So reaction is degree of reaction defined as your drop in moving blade divided by fixed blade plus moving blade. So in this case it will be, in moving blade is 40, so 40 by 40 plus 30 will get 4/7. So the answer is option A. So we'll see some numericals on this. So we have a steam power plant operating on a simple idle Rankine cycle. So the steam power plant is given, shown below. You have all 4 components listed, and the steam turbine enters the turbine at 3 megapascal and 350 degrees Celsius. This is 350 degrees Celsius as shown in the figure 3. It's 3 megapascal and 350 degrees Celsius, and is condensed in the condenser at a pressure of 75 kilopascal. So from 3 megapascal it's reducing to 75 kilopascal, and this heat is supplied to the steam in a furnace maintained at 800 Kelvin. So the boiler, you are getting steam, the heat source for the boiler is at temperature of 800 Kelvin, and the waste heat is rejected to the surrounding at 300 Kelvin. So in the condenser, the heat which you are rejecting to the ambient, it is at 300 Kelvin. So determine the exergy destruction associated with each of the 4 processes and the whole cycle. So each of the 4 processes is for the 4 components. So constant pressure heat addition, constant pressure heat rejection, and isentropic compression and expansion. So that is the 4 processes. We need to find what is the exergy destructed in each of those 4 and as a whole cycle. And we also are asked to find out the second law efficiency of the cycle. Okay, so we'll see how to solve this. So for our ideal Rankine cycle, the first is simple. We can find out each of for the given condition, we know 0.3 the maximum temperature. For isentropically, we can find out constant we can find out entropy at state 3. So using that, we can find out S3 will be equal to S4. So you can find out the dryness fraction here and enthalpy here for 75 kilopascal pressure, and then we can find out state 1, which will be at saturated liquid condition, this being ideal Rankine cycle, and then we can use the velocity specific volume at state 1 to find out state 2 and the enthalpy at state 2, and we know all the 4 enthalpies. After that, we can find out each of the components heat transfer and work transfer. So Q in will be 2729 kilojoule per kg, and the work done in the pump will be 3 kilojoule per kg. The work done in turbine which is going out, so turbine is 713 kilojoule per kg. So 3 kilojoule in pump and turbine is 713. So in Q out is 2019. So that's each of the quantities, and if you see the efficiency of the cycle is then W net, so 713 minus 3 divided by 2729 will give you 26%. So the ideal Rankine cycle operating between 3 megapascal and 75 kilopascal at 350 degrees Celsius is 26%. So now, how to find out exergy destructed in each of the processes. So we know that process 1, 2 and 3, 4. You see, 1, 2 is the pump and the turbine, 3, 4 is the turbine. So these are isentropic processes. So there is no entropy generation, and there will be no exergy destructed. As I told in the previous slide, exergy destructed will be T naught, the ambient temperature or the dead state temperature, into entropy generated. So this being isentropic and adiabatic, reversible. So there will be no heat transfer and there is no entropy generation. So this will be 0, and therefore will not have any irreversibility. So exergy destroyed will, in case of 1, 2, process 1, 2 and process 3, 4 will be 0. Process 2, 3 and 4, 1 is the heat addition and heat rejection process. So this is happening at constant pressure, and in this case, this being an ideal Rankine cycle, so we are assuming the internal irreversibilities are not there. So this will be internally reversible. So as such in just the boiler there will be no exergy destroyed, just because of the boiler. So it's internally reversible, but because the heat transfer is happening between temperature difference, because heat can transfer can happen only if there is a temperature difference. So this is at 800 Kelvin, so there will be some irreversibility because of that. So how if you see the entropy of the can calculate the entropies at state 2 and 3 and 1 and 4. So S2 equals to S1, so we can calculate the entropy at state is 1.2132. So S4 equals to S3, the same value is 6.450. This is at 75 kilopascal and this is at 3 megapascal and 350 degrees Celsius. And so the exergy destroyed is T naught into S generated. So S gen, this you can get it from an entropy balance. So the fluid coming in, if I take this process 2-3, so S3 is the fluid going out equals S gen plus what is coming in. So S2 S3 equals S gen, the entropy generated, plus Q in by temperature at which the temperature is happening, Q in by T. So Q in by 800 plus S2. So that will be the entropy balance across the boiler. So if you see from there you can write S gen. You need to take the terms on the right hand side. So you'll get S3 minus S2 minus Q in by T. That is just fluid going out minus entropy of fluid coming in plus the entropy generated because of heat transfer. So S3 out minus entropy because of fluid coming out minus in, and the entropy because of heat coming in. So S3 minus S2 by Q by T. We have found out Q in. So substituting the values, we will get 636 kilojoule per kg. That is the exergy destroyed in case of boiler. And if you see in case of same is the process for finding for condenser. In this case the out will be the in. So this is 1.2132 minus 67450 and 2019, because it's going out, that will be positive. So 2019 by 300. So this will come out to be 360 kilojoule per kg. So 636 is the exergy destroyed in the boiler and 360 is the exergy destroyed in the condenser. So irreversibility, total reversibility of the cycle is each of the components exergy destroyed. So for 1, 2 and 3 and 4, for turbine and pump it will be 0, and you need to just add what is destroyed in case of condenser and boiler. So 636 plus 360, which will give you 996 kilojoule per kg. And so that is we have found out that. So next is the total exergy destroyed during the cycle could also be determined from this total. If you consider this whole thing as a black box, this being a closed cycle, so if you see there is only work coming out, Q going in and Q coming out. So if you apply for the whole cycle, if you put up this thing, so there are only 3 components. One is work, one is heat transfer in, one is heat transfer out. So work will not generate any exergy or entropy difference will be zero, entropy generated will be 0 because of work transfer, and only entropy generation will be because of the Q in and Q out. So that exergy destroyed can be because Q which is coming out minus coming in. So Q out by TL minus Q in by TH into T naught. That's the expression. So that is exergy, total exergy destroyed for the cycle, and that will same as what we calculated the previously. It will come out to be 996 kilojoule per kg. See, if you see in this case, so if you add this exergy destroyed 2, 3 and 4, 1, S3 and S4 will cancel out, S2 and S1 will cancel out because both are same. So this will reduce to Q out by T sink minus Q in by T source into T naught. So that's what we got here. So in this case, if you see, the largest exergy destroyed occurs because of the heat addition process. It's 636 compared to 360. This is a higher value, so this boiler is contributing a higher heat exergy destruction. So if you reduce this exergy, you can make the system more efficient. So how to do this is, in ideal case, what we discussed in the previous week, raising the turbine temperature, superating the steam to higher temperature, or increasing the condenser pressure. So these are all some cases which we saw, and we also saw some numericals on that, how each of it is having an effect. So that is increasing it to a higher temperature, we saw that it was becoming more efficient. So that process will also, what's happening is, your temperature of the source is at a higher temperature, but you are not fully utilizing that to convert the steam. So now raising the steam's temperature close to this source temperature, you are avoiding or minimizing the exergy which is destroyed in the boiler. So doing so, you can make this more efficient. And the part B of the question was to find out the exergy second law efficiency, or the exergy efficiency. You can say second law efficiency is called exergy efficiency. So the second law efficiency is defined as exergy recovered by exergy expended. So exergy recovered is what you get, and exergy expended is what you have spent on exergy spent on the process. So this is 1 minus the exergy destroyed by exergy expended. So if you see, the exergy is expended because what you are giving in the exergy which you are giving in is the pump work and the heat. So that is what you are giving in. So the exergy of those are exergy of pump is 3 kilojoule per kg, which we already calculated. So that will be equal to the exergy of the pump, and the exergy of the boiler will be 2729 minus 636. The boiler, if you see, exergy will be Q in minus exergy destroyed. So exergy of boiler is Q in is 2729 and exergy destroyed is 636. That will come out to be 1706. So this will be equals to 1709. Here I have shown you another case of how to calculate that. So 1 minus T naught by TH. If you see, this is Carnot efficiency, and if you run a Carnot cycle between the heat source temperature and the ambient temperature, so what is the maximum work? That is equals to the exergy. So you can calculate that way, or else if you multiply Q in, it's the same as what I told, the heat source temperature minus the exergy destroyed. Exergy destroyed in boiler was Q in to T naught by TH and the other part. So So exergy heat in is 1706 kilojoule per kg. So I have added that to the pump, so that is exergy expended. And what was destroyed, as already we have already calculated, is 996 kilojoule per kg. Can substitute it directly. So it's 1 minus 996 by 1709, or exergy recovered is the useful work which you have got, just 713. So this will come out, both will be same, it will be 41.7%. So the second law efficiency is 41.7%. Is this clear? Okay, so moving on. So I have taken a nozzle example. So steam enters a converging diverging nozzle at 2 megapascal and 400 degrees Celsius with a negligible velocity and a mass flow rate of 2.5 kilojoule per skin, and it exits at a pressure of 300 kilopascal. So the flow is isentropic between the nozzle entrance and throat. So they have given your that you have a converging and diverging nozzle, and your pressure at your inlet is 2 megapascal, and your temperature is 400 degrees Celsius. So your velocity is negligible, so V1 you can neglect, and the mass flow rate is also given 2.5 kg per second, and from 2 megapascal it's expanding to 300 kilopascal, and flow is isentropic. So nozzle efficiency is given as 93%. So the first case is you are asked to find out the throat and exit areas, and second is the Mach number at the throat and the nozzle exit. So we need to find the area and Mach number at throat and the exit. This given is a converging diverging nozzle. Okay. So we know that as the inlet velocity is negligible, so your stagnation condition will be same as your static case, because the stagnation is just the static plus the dynamic, what you are getting because of the velocity. As this case your velocity is negligible, your stagnation condition will be equal to the static condition. So inlet stagnation and static states are identical. So the ratio of this exit to inlet stagnation pressure is, we know exit pressure as 300 kilopascal, which was given, and your stagnation pressure at inlet, or your normal pressure which is given, because both are same. So that will be 2 megapascal, so 2000 kilopascal. So 300 by 2000 will give you 0.15. But if you see a critical pressure ratio is given as P star by P naught into 2 by K plus 1, or by K minus 1. For K will be 1.3 for steam. So when you substitute this, you will get this critical pressure ratio as 0.546. If you see, so this pressure ratio which you are happening in the converging diverging nozzle from 2 megapascal 300 kilopascal, this is at 0.15, which is less than this 0.546. So what this critical pressure ratio says is, if you go to 0.546 pressure ratio, it will reach Mach number 1. So in this case you will have a supersonic exit, because this is less than the pressure critical pressure ratio. So we know that this will have a supersonic velocity at the exit. So we also know that at throat you will have Mach number 1. So at throat condition we'll find out the pressure. So Pt by pressure at the inlet, we know that pressure ratio is 0.546, critical pressure ratio. So 0.546 into the stagnation pressure at the inlet, which is 2 megapascal, we'll get 1.09 megapascal. So that is the pressure at the throat. So now what we know is at inlet we know 2 megapascal, and we also know your temperature 400 degrees Celsius. So correspondingly your enthalpy and entropy values will be 3248.4 kilojoule and 7.1292 kilojoule per kg. So this is the values for the steam at the inlet for 2 megapascal and 400 degrees Celsius. Now when this passes through the converging section and reaches the throat, we know that this is happening isentropically, so your entropy will be same. Since ST throat enthalpy is same as your inlet enthalpy, entropy. So for that, and pressure of 1.09 megapascal, which we calculate using the critical pressure ratio, we know the enthalpy and specific volume is also is calculated. So we know both. So now velocity is we know your stagnation enthalpy. So initially at h1 equals, we do energy balance here, h0 1 equals h1 h throat section plus the velocity square by 2. So the steady flow energy equation is basically. So inlet velocity will be negligible, so that is h inlet enthalpy equals outlet enthalpy plus v square by 2. So rearranging that, we can find out the velocity at the throat. So we know h01, which is 3248.4, and we also know the throat section, the enthalpy at the throat section. So on substituting that, we get the velocity as 585.8 meters per second. So using this, and we know that here we can calculate area, we know specific volume, and the question is also given that mass flow rate is 2.5 kg per second. So mass into a specific volume divided by velocity will give me area at the throat section. So A into V is the volume flow rate. So area we will get from area mass of the steam into specific volume divided by velocity. So we know mass 2.5 kg per second. We know velocity at the throat section 585.8, and we also know specific volume 0.242. So on substituting this, we get the throat section area as 10.33 centimeters square. So and second, at state 2s is at the exit condition, assuming an isentropic expansion throughout the nozzle. So state P2 will be we know that is 300 kilopascal, and entropy at state 2 will be equal to entropy at the state 1. So is 7.1292 kilojoule per kg Kelvin, and for this condition, pressure and entropy condition, we can find out the enthalpy, which will come out to be 2783.6 kilojoule per kg. So the enthalpy of the steam, we can we assumed that it's expanding isentropically. So we know from the problem that the exit pressure, the nozzle is overall efficiency is 93%. So the nozzle efficiency is defined as the stagnation enthalpy at state 1 minus the enthalpy at state 2 divided by enthalpy at state 1 minus state 2, assuming an isentropic flow. So we know H01 and H2S on substituting, and we also know the nozzle efficiency, which is 0.93, and the stagnation enthalpy at the inlet is 3248, and H2S is 2783. So on substituting, we'll get H2S 2816.1. So after that, we know the conditions, enthalpy and pressure So using that we can find out the entropy and also the velocity. So velocity is specific volume. So specific volume is 0.67723 and the entropy is 7.2019 kilojoule per kg. So now, so the exit velocity and the exit area will be, so V2 is 2 into H0 1 minus H2. So the same what we saw the previous case. So we know the H01, the stagnation alpine inlet, and H2 also we have calculated. So on substituting this, we'll get 929.8 meters per second. So on substituting the mass and specific volume and velocity, we can find out the area, which will come out to be 18.21 centimeter square. So the cross section area is 10.33 centimeter square and the exit area is 18.21 centimeter square. So the second part of the question was to find out the velocity of sound and the Mach number at the throat and the exit of the nozzle. So for that, finding Mach number, we need to find out the sonic velocity or the velocity of sound. For that, C is defined as square root of dou P by dou rho. As we cannot find direct, we don't have any pressure relation directly, so we will convert this into differences. So it will be delta P by delta 1 by V, the specific volume. So density is 1 by V. So substituting that. So using this differences, we can find out the sonic velocity. So what we are doing is for throat section, for a at throat section where your Mach number is 1, your pressure is 1.09 and megapascal, and you know the entropy. For that condition, what you are doing is you are taking a small increment in pressure on both sides. So you are taking 1.115 and 1.065, assuming 25 kilopascal difference. So at that corresponding difference in pressure, what is the difference in specific volume, reciprocal of specific volume? So at 1115 kilopascal, you are having 0.23776 specific volume, and correspondingly 1065 is 0.246. So substituting these values, the velocity of sound is 584.6 meter per second. So if you substitute, you can see that Mach number is 1. So the small difference is because you are using that differences and not the exact differential. Because of that you are getting, but this is 1, you can assume this is 1. So what we have calculated is correct. So at throat section, the velocity which we have given, 585.8, is the sonic velocity, which is true. At throat section you need to have Mach 1. We'll have 1. So we now know the sonic velocity value. So now at the exit, what will be the sonic velocity at the exit? So it can be determined. We know the entropy value at the exit, which is 7.2019 kilojoule per kg, and the pressure is 300 kilopascal. So we take the same increment in pressure. So we take 325 into 75 kilopascal, and we calculate the sonic velocity. And on substituting, we get the velocity as 515.4 meter per second. So this is the velocity of sound at the exit condition of 300 kilopascal and the entropy value. So we know Mach number is velocity by the velocity of sound. The velocity at exit we calculated as 929.8 meter per second, and the velocity of sound is 515.4. As you see, this being a converging diverging nozzle, the exit is supersonic, and we get a value of 1.804 for Mach number at exit. So we have calculated all the area and the Mach numbers. In this case, we didn't have pressure, so we used differences in pressure, assuming that will give you the slope. You can take a smaller value also, but this is taken based on for readings which will be available in the table. So is this clear? So these are the questions I have prepared today. If you have any other questions, you can ask. Even if you have any doubt in the previous weeks, you can ask any doubts on that. Yeah, actually the slides are being shared. If you go to the sheet which is given in the NPTEL page, you see the live section, it will be directed to a different Excel sheet or something. So in that, the links for all the slides and the videos are provided, so you can access from there. In this case, there are some mistakes are there in the slide. I'll edit those and I'll put it on. You can access it. I think tomorrow or day by tomorrow, you'll get the slides. If you don't have any doubts, you can close the session. If you have any doubts regarding this week or the previous week, you can ask.